Hello, welcome to video 41 in the lecture Advanced Mathematic Modeling. So we were discussing how to estimate the critical exponents if we have a long tail or power law distribution, and we discussed this with graphical method, with histograms and all the tricks and pitfalls that can happen if you make these histograms of long tail distributions. And in this video I want to show you another way how you can estimate the critical exponent just by calculation with a maximum likelihood method. Okay, so let's say we start with our power law distribution, which we write it down again. It looks like this. The probability P of x is alpha minus 1 over x0, the cutoff value, times x over x0 to power minus alpha. And so here you see I've already included the normalization because this will be important. We need this later. But this is the same way we wrote our distribution always before. Okay, and now assume we have a we have a sample. A sample of n data points. So we have our xi, and I runs over 1 to n. And in the previous video we just made a histogram of this, or we made a rank plot of this, and now we want to use the maximum likelihood method. And so now we could say, what is the probability that if, so we want to calculate the probability, that's a capital P, this was the small p of our distribution, the probability to have this sample, to achieve the sample, given we have chosen a certain exponent alpha. So what would be this probability? So it would be the product to have the p of all the xi's, and we run from I equal 1 to n. Right? Because like every value of our sample, yeah, has a certain probability to be realized. That's the probability. That's just our distribution, and we have n points, so we have to multiply all these probabilities, and this gives us the probability if we just take n realizations from this distribution with a certain alpha. That's the probability to exactly get the sample. And now we can put in this formula here. So we have the product I equal 1 to n, and now we have this alpha minus 1 over x naught times xi over x naught to minus alpha. And we call this, the likelihood of our sample. But this is not really what we are looking for. We are looking not for this likelihood, because our what we really we want to estimate the critical exponent, what we want to have actually is different. So that's a conditional probability, right? So conditional probability given a certain alpha, what's the probability or the likelihood to have the sample? But we are actually interested, what is the likelihood or the probability to have a certain alpha given our sample? Yeah, because the sample, that's our information, and we want to know what's the best alpha. Which alpha maximizes this probability? Yeah, given the sample, what is alpha? Right? So we are interested in this conditional probability, but what we can calculate very simple is this given alpha, what's the probability for the sample? And now we can use the Bayes rule, so we can convert this conditional probability in here, this reversed conditional probability. But then we have to multiply by the probability of alpha divided by the probability of x. Yeah? And this was if we use Bayes rule. So, and then, okay, this we can calculate, but now it's the question, what are these two probabilities? The probability of x and the probability of alpha. And now the probability to have a sample, I mean this is fixed. Because we have already the sample. Already. Yeah, whatever this is, this value, this p of x, doesn't depend on alpha anymore. So basically what I want or let's look for what's the the strategy. We want now to find this alpha which maximizes this conditional probability. And so the alpha which has the highest likelihood, then we say that's the alpha we will estimate. And so we need to maximize this function. We need to find, this is a function of alpha, and we need to find this alpha which maximizes this. And we want to maximize this, so we have to maximize all this here. And so we see this here doesn't really depend on alpha, so we can just forget. That's just a constant which can forget. Now the problem is, what is this p of alpha? So that would be the intrinsic probability of a certain alpha. That's kind of difficult, and that's always this problem in all the Bayes calculations. So we need a prior knowledge about which alphas are more likely than others. So this is kind of difficult in a kind of philosophical or interpretation sense. But what we can say without further information, we could say that all alphas in this exponent are intrinsically equally probable. Without further information, all alpha equally likely. Or we could say at least in a certain range, because like we know alpha smaller than 1 we get problems here. So then we can say, we just set this p of alpha to 1 and say the intrinsic probability for all alphas is constant, is 1. Yeah? And then, you know, we just when we want to maximize this, we just have to maximize the likelihood of the sample. And now, and that's the basic philosophy in all this maximum likelihood approaches here. So we want to find these parameters here, which are which have the highest probability given the sample, and we just calculate here the likelihood of the sample given the alpha, the parameters. And now so that's the philosophy, and in order to make the calculation more simple, there is a kind of trick. To simplify the calculation, we calculate this L. This is the logarithm of the likelihood. And this is called the log likelihood. And this that we use here, the logarithm of the likelihood, that's just a technical trick to calculate to simplify the calculation, because we want to maximize this, and we will see this is more easy with the logarithm of the likelihood. Whereas the other things here to deal with these probabilities P of alpha and P of x, that's a more interpretational issue, and here now you can discuss for hours what would be this P of alpha. Okay, and so now let's calculate this log likelihood. So so we have to take the logarithm of this formula here, and then this is, now we have here a product, and the logarithm of the product is the sum of the logarithms. So that's the trick, so that instead of the product we have a sum, which we can handle better. So we have now a sum of I equals 1 to n, and now we have so the sum of all the terms here, and then you see every term is again a product. So we have the logarithm of this minus the logarithm of this plus the logarithm of this. So we have here the logarithm of alpha minus 1, then we have minus the logarithm of x naught, and now the logarithm of something to power is the power times the logarithm. So then the power is minus alpha, and then the logarithm of xi over x naught, and then we close the parentheses. Yeah? And so what we've done here, we just have taken the logarithm, and then the product is modified into a sum. Okay, now we can look a little bit. We can simplify this sum. So the first term doesn't depend on the index I. So the first is just n times the logarithm of alpha minus 1. And then here again we have n times the logarithm of x naught, and then minus alpha. And now we have to sum these terms, the sum of the logarithms of this ratios xi over x0. And so that's the log likelihood. And now we want to maximize this. So we want to find this parameter alpha with maximal. So actually we want to have the maximal likelihood. Yeah? But since the logarithm is a monotonous function, so this alpha which maximizes the likelihood, that's alpha will also maximize the log likelihood. So it's okay if we maximize the log likelihood, then we have also maximized the likelihood. So find alpha with maximal log likelihood. And how do we find the value which maximizes a function? We need to take the derivative. So we have to calculate the derivative of the log likelihood by alpha. And now let's see what's the derivative. So we have here n times the derivative of the log is 1 over the argument. So we have here n over alpha minus 1. So here the derivative, this constant just disappears. And now we take the derivative of this here, then just the constant alpha, this alpha goes away. And this is minus the sum of logarithm xi over x0, and this sum runs from I to n. So that was just the derivative, and now the derivative has to be set to 0 to have a local extreme value of L. And now we have an equation which is so the left hand side of this is this combination is 0. And we can solve this for alpha. And then if we solve this for alpha, then alpha is given 1 plus n times the sum of the logarithm of xi over x0. The sum runs from I equal 1 to n, and the whole thing to power minus alpha. And so you see we have a kind of average that we have to do here when we want to calculate our most likely exponent. So we have all our samples, we normalize them by the cutoff, take the logarithm, so here we average, but then we need now to divide or by 1, so like that's so actually we could also so you see this, and it's just an average, so you have the average value of this logarithm of xi over x0, and this gives us the estimation of alpha minus 1, so the critical exponent is 1 plus this here. Yeah? And this is a simple formula. Yeah? So just if we have given our sample, yeah, we just can plug this in, calculate this, and then we obtain our alpha. Yeah? So that's the way to calculate optimal parameters with maximum likelihood method, and this here is for the power law distribution. And in a similar way, you could also, for example, if you have an exponential distribution or another distribution and you have some parameters, you could use the same kind of idea, use this log likelihood approach to obtain the optimal parameter, which gives the best estimation of these parameters, so that a sample describes this distribution. And so now in practice, if you have a sample here, my recommendation would be construct the histogram with log-sized bins. Here, calculate here the slope by straight line fit to see what's the order in the slope, what kind of, look for scaling regime. So what is the slope that you think here from the graphical analysis? And then additionally use the log likelihood method to calculate this critical exponent, and then compare the two, and then see what does this slope from the straight line fit, how does this relate to the slope that you calculate from the log likelihood method. In doubt, you can trust this more. So, and actually if you look in the literature, there's also ways to calculate here some estimations, some errors about this alpha. But I would not trust this alone, because when we do this formula, we already assume that our data are power law distributed. But what do we know about this? So like this will always give some value of alpha. So we need to also to make this plot to see that we really have a scaling. If you make this histogram and the curve is very, so it's not a straight line, the points don't lie on a straight line but are very curved, then the whole calculation with this log likelihood doesn't make sense at all. Yeah? So only if we have here a certain scaling regime, then we can use this formula. And for example, if you see you have scaling only in a certain range, maybe something like this, and then the scaling decays, or you have a different scaling in a different range, this means maybe we should have started with a different distribution in the first place, or maybe we could restrict data, we could restrict our sample to a certain range where we have a scaling. So this means maybe not all data points from the sample should enter in this calculation here. Yeah. So in short, so use both, use the log likelihood method and make the plot of the histogram. Okay, that was it for estimating critical exponents. In the next video, I want to discuss a bit about what's so special about this power law distributions. So why are we like, I mean, there's many different long tail distributions. Why is such a special focus on distributions which have exactly this form? This we will discuss in the next video. For now, thank you.